Alright, hi everybody. So we're in section 4.3. We've been talking about maxes and mins, inflection points, looking at all those features on a graph. Now we're going to look at how derivatives affect the shape of a graph. So we're going to be looking at these concepts, dealing with them a little more algebraically this time, but also looking at them graphically as well. So when we're talking first about f prime, that first derivative, so this tells us slope, right? That's what the derivative gives us, is the value of the slope. So if the derivative is positive, that means that the graph has a positive slope at that point, and when f prime is negative, that means that it has a negative slope at that point. So we use the terms increasing or decreasing to describe this growth, whether the graph is growing up or down. Right, so on this graph, for example, from A to B, this graph is increasing. That means that f prime must be positive. From B to C, it's decreasing, so f prime must be negative. And then from C to D, again, we're increasing, so we have that f prime must be positive. Okay, so when we're looking for determining whether a function is increasing or decreasing, we're looking at the first derivative. So in order to determine where the first derivative is positive or negative, we need to find those points where the derivative is 0, and then determine, either to the left or to the right of those zeros, what is actually happening. Is the graph going up or going down? So to determine when a function is increasing or decreasing, we're going to compute f prime and get those critical numbers. Right? Those critical numbers are where the derivative is equal to 0. We're going to put the critical numbers on a number line and then pick a test point in each of those intervals to determine if the derivative is positive or negative on those intervals. Okay, so let's go ahead and look at this example here. So we have f of x equals that function. Determine where f is increasing and where it is decreasing. Alright, so let's get the derivative here. So f prime of x, that's going to be 12x cubed minus 12x squared minus 24x, and then plus 0. So just using the power rule a lot on this one. Okay, so to determine where this is equal to 0, we need to start factoring. So that's going to be, I can factor out a 12x from everything. That leaves me with an x squared minus x minus 2. And then that term is also factorable. So that's going to be x minus 2 times x plus 1. And we set that equal to 0. And that's going to give us 3 x values. That gives us x is 0, 2, and negative 1. Whoops. So 0, 2, and negative 1. So now if we look on the number line here, let's go ahead and mark these on here. It doesn't have to be perfectly spaced. We just need to know where the numbers are. So negative 1, 0, and 2. And then we're going to pick a test point on each of these intervals to determine whether the derivative is positive or negative. Okay, so 1 point from each of these intervals. You always want to try to make it as easy on yourself as possible. Don't pick really complicated points that make your work harder. So like I'm going to pick negative 2, negative 1/2, 1, and 3. Right, just the easiest numbers that I can work with. And then we check each of these in our derivative to see whether they are positive or negative. So, and if we did that, we get f prime of negative 2, right? So plug that in, that would give us a negative times a negative times a negative. So that would actually become positive. F prime of negative 1/2. That would be negative times positive. So that's less than 0. F prime of 1, we get positive times negative times positive. Oops. So that one is going to be less than 0. Okay. Then get my last one in here. So f prime of 3, that's going to be positive, positive, positive. So we get f prime of 3 is bigger than 0. It doesn't even matter what the specific value is. All that matters is whether they are positive or negative. So we have anything less than negative 1, positive. Between 0 and negative 1, we get negative. Between 0 and 2, we get negative. And between, and then just above 2, right, 2 to infinity, we get positive. Okay, so then for this one, I also like on the number line to go ahead and just draw a little arrow indicating, the direction that the graph is headed. Because that can give us more information about maxima and minima that we'll see in just a little bit here. Okay, so we can see where the function is increasing is from negative infinity up to negative 1, and from 2 to infinity, and it's decreasing from negative 1 up to 2. So when it comes to testing for local maxima and minima, well, remember a local max is a point such that all values around it are smaller than it, right? So in order for it to be a maximum, we have to be increasing into it and then decreasing out of it, right? Because that would look something like, increasing into it, decreasing out of it. That would be a local max. And then for a min, we'd have to be decreasing into it and increasing out of it. And that critical point down there, that would be our min. So, when we look at how we're going to actually test for maxima and minima, this is what we call the first derivative test. So this says, suppose we have a critical number at c. If f prime changes from positive to negative at c, then we have a local maximum. If f prime changes from negative to positive, then we have a local minimum. And if f prime does not change sign, then it has neither. Okay, so again, we go from increasing to decreasing, that's a max. Decreasing to increasing, that's a min. And if we go, like in the previous case, right, we saw one case where it went from decreasing to decreasing, right? So it leveled off, but then just kept decreasing. That would not be a max or a min. Okay, so and here's again kind of the graphs of what we're looking at. Okay, so we have the local min decreasing to increasing, local max increasing to decreasing. So let's look at the same example. So use that number line that we created. So we have negative 1, 0, 2. We have plus, minus, minus, plus. Right, so increasing, decreasing, decreasing, increasing. This is why I like drawing the arrows on here, because you can see pretty quickly the shape of this graph is going like this, still decreasing here, but then switches to increasing. So you can identify a little bit faster where the max and min values are. So we would have a local max at x equals -1, and a local min at x equals 2. And then, of course, at 0, we go from decreasing to decreasing. So that doesn't give us a max or a min. All right. So now let's keep going. Talk about the second derivative. So for the second derivative, remember this one tells us whether f prime is increasing or decreasing. So it's talking about how the slopes are changing. So not just is the graph going up or is it going down, but are the slopes getting higher? Are the slopes getting lower? So it tells us more about the bend of the graph, right? So this tells us about whether the graph is bending upward or bending downward. Okay. So let's look at an example here, see kind of what we're talking about. So consider functions with the graph shown. For each of these functions, draw the tangent lines at 1, 2, 3, 4. And it's asking, is the derivative increasing or decreasing over this interval? And then what about the second derivative? Okay, so let's draw a bunch of tangent lines here. So here at 1 on this first graph, there's our point, there's our tangent line, our point, our tangent line, point, tangent line, point, tangent line. So it's asking, what is the derivative doing? Well, this tells us that f prime is positive, right? F prime is greater than 0 because the slopes are all positive. But the derivative here, is it getting larger or smaller? Well, we go from a little more flat to a little more steep. So we say f prime is increasing. So that means f double prime must be positive. Okay, so f prime is increasing. The slopes are getting larger, which means that the second derivative must be positive. And then for the second one, so if we look at some tangent lines over here, so this one's a little different because we have a graph that goes from decreasing to increasing. But if you think about what the slopes are doing, this slope here, this first one, is really negative, getting less negative, getting to 0, and then becoming positive. So f prime in this case is also increasing, which means that f double prime is positive. And then for this third one, graph our tangents. So and hopefully you can start to notice the pattern here, that these tangent lines are starting to get smaller in slope, right? They're starting to get lower, less steep, more flat. So in this case, f prime is decreasing, which means that f double prime is negative. Okay, so the slopes are getting smaller. Okay, and then same thing for this one. If you look, even though the function is increasing, right, the slopes are getting more shallow, getting smaller, hitting 0, and then becoming negative. So in this case, f prime is decreasing again, which means f double prime is negative. All right. Now, the terminology that we use to describe this bend, this second derivative relationship, is called concavity. So we say the graph of a function is concave up on an interval if it bends upward as we move from left to right, and the graph of a function is concave down if it bends downward. So again, we're not talking about it increasing or decreasing, right, going up or going down. We're talking about how it's bending. So a concave up graph looks like this one. Concave down looks like this one. And so generally the way that we can remember this, concave up, so it's abbreviated CU, it looks like a U. That's the concave up graph. And concave down is the upside down U, that's CD. All right. Now, when we're using concavity to find maxima and minima, this is where we can start to use the second derivative to help us as well as the first derivative. So the concavity test, if f double prime is greater than 0, then the graph is concave up. If f double prime is less than 0, then the graph is concave down. So when we're dealing with concavity, it's always related to the second derivative. So if f double prime is positive, the graph is concave up, and if f double prime is negative, the graph is concave down. Okay, so to make this determination, we find where the second derivative is equal to 0, and then we can just do the same thing we did before. On the number line, determine where the graph is concave up and down around these points, where it's 0. Okay, so here's our same function we've been working with for this section. So let's go ahead and find the second derivative. So first we need f prime, which we found earlier. That's 12x cubed minus 12x squared minus 24x. And then we'll get f double prime, again using the power rule. That's going to be 36x squared minus 24x minus 24. And then we need to see if we can factor this. So you can pull a 12 out of everything. Leaves us with 3x squared minus 2x minus 2. And this, unfortunately, is not very factorable. So we do need to check. You can try completing the square on it, or you can use the quadratic formula, which is what I'm going to do. So we get x equals negative b, so that's negative 2. Okay, so that's 2 plus or minus the square root of b squared, so that's 4, minus 4ac, so that's 4 times 3 times negative 2, so that's going to become a plus. That's going to be 24 over 2a, so that's 6. So that's 2 plus or minus root 28. That has a factor of 4 in it, right? So that's 2 root 7 over 6. So that's 1 plus or minus, 1 plus or minus root 7 all over 3. And of course this gives us two answers. The plus and the minus are two separate values. So we're going to have the 1 minus root 7 over 3. And then the 1 plus root 7 over 3. Okay. And then we would need to determine what is happening in between all of these values. So we would go ahead and pick any numbers we want to the left and to the right of these. So you can check on your calculator and see pretty quickly what numbers are allowed for us, but I went ahead, let me do a different color. I went ahead and checked at f double prime of negative 1, f double prime of 0, and f double prime of 2. And it gave me a positive, a negative, and a positive. So we get concave up, concave down, concave up. Okay, so that's going to give us the intervals of concavity. That tells us where the graph is bending up and bending down. So again, this has no relationship to whether the graph is increasing or decreasing, right? That's totally separate, so we need to just bear that in mind. So now, inflection points. An inflection point is a point on the graph where the graph changes concavity. An inflection point is a point on the graph where it changes concavity. So it goes from either concave up to concave down, or from concave down to concave up. All right, so it's similar in computation as a max or a min. So we're checking where the second derivative is equal to 0, determining if it changes from concave up to down, or vice versa. So in our previous example, we found that f double prime of x equals 0 at x equals 1 minus root 7 over 3 and 1 plus root 7 over 3. And we saw on the previous page here that we switched from concave up to concave down, and then concave down to concave up. So these would be inflection points. So we have, so let me just say, since concavity changes at these points, we have inflection points, which are abbreviated IPs, at x equals 1 minus root 7 over 3 and 1 plus root 7 over 3. So we have those two are both inflection points. Now, how do we use this second derivative to help determine max and min values? Well, if you remember the graphs of the concavity, right, so a concave up graph looked like this. Ooh, almost like that. It looked like that, like a U. Right, this is concave up, and concave down looks like that. So if we're trying to determine if something is a max or a min, so if we know that we have a critical point at C, and f prime of C is positive, what does that mean? If double prime. If f double prime of C is positive, then this means the graph is concave up. And if it's concave up, then that means our critical point has to be this point down here. And so that would be a local minimum. So if f prime is equal to 0 and f double prime is positive, the graph is concave up, so the point in question is a minimum. And then if we have a critical point and f double prime is less than 0, so similarly, right, being less than 0 means the graph is concave down, so our critical point must be there at the top. So that's going to be a local maximum in this case. Right. The only thing about the second derivative test that we just have to be careful with is that if f prime of C is 0 and f double prime of C is also equal to 0, then the test fails and gives no information. So it's inconclusive if we have the second derivative is also equal to 0, because that tells us that it's also an inflection point, and then we need more information. So at that point, we would just go back and use the first derivative test instead. Okay, so again, concave up means we're at the bottom, we're at the minimum. Concave down means we're at the top, so we're at a maximum. So use the second derivative test to test each of the critical numbers for local maxima or minima. So we found previously the critical points were at x equals -1, 0, and 2. So we have f double prime of x. So let me just remind us what that one was. So this was 36x squared minus 24x minus 24. So f double prime of -1, f double prime of 0, and f double prime of 2. Okay, so now again, with these tests, it really doesn't matter what the value is necessarily. All that really matters is whether the graph is positive or negative there, if the second derivative is positive or negative. So at -1, let's see, we get, that stays positive 36, that becomes positive 24 minus 24, so that's going to be positive. And then f double prime of 0, that's going to be 0 minus 0 minus 24, so that's negative. And then at 2, we get 36 times 4 minus 24 times 2 minus 24. This one, is positive as well. All right. So we have a graph that is looking like this. So it's going concave up, concave down, concave up, something like this. So you have local min, max, and then min. So we have local min at x equals -1 and x equals 2, and local max at x equals 0. So now we can use all this information from these previous parts to help fill in this graph. What I'm going to do is, because we have the technology here, I'm just going to use Desmos instead of sitting here and plotting out all the points on here. But you could just plug in points into the original function, plot those out. But let me go ahead and just put this in here. So y equals 3x to the 4th minus 4x cubed minus 12x squared plus 5. And this does seem to match with our assessment here, right? So we've got our min, our max, our min, and we can identify inflection points in there as well as being in between -1 and 0, right? So somewhere in the middle here, and then another inflection point somewhere in the middle here, where we're changing from concave up to down, and then down to up as we move along the rest of the curve. All right. So let's move on. We're going to pass over this example. Let's look at this example. So we have the function f of x, and we're given f prime and f double prime. So for this one, we need to determine where it's increasing and decreasing, find those local maxes and mins, and then we'll look at the concavity, and then of course the graph. So let's see here. So for increasing and decreasing, we need all the values where it's equal to 0 or does not exist for our first derivative. So I know it's equal to 0 when x equals 4, right? Because that would give me 4 minus 4 is 0. And then I also know it cannot be at 0, right? It does not exist at 0. And also cannot exist when x equals 6. So those would be our critical points. And then we test to the left and to the right of each of these critical points. So we pick something less than 0, say -1. That's going to give us a negative. Plug in something between 0 and 4, pick 2, 3, whatever you want. That's going to give us a positive. Between 4 and 6, so maybe pick 5, that's going to give us a negative. And then something bigger than 6 will also give us a negative. So we go from decreasing to increasing to decreasing to decreasing. So in determining local maxes and mins, based on this information, we have a local max at x equals 4 and a local min at x equals 0. Okay, and I would be using that first derivative test. And then for the concavity, determine where it's concave up and concave down. So the inflection points are going to occur where the second derivative equals 0 or does not exist. That's going to occur when x is 0 and when x is 6. Okay, so the numerator produces no inflection points for this one. So we get 0 and 6. Test concavity to the left and to the right. So plug in a test point into the second derivative, and we get concave down, and concave up. Okay, so if we were asking for inflection points, then we would have an inflection point at x equals 6, because again it changed concavity, went from concave down to concave up. Not at 0, because it stayed concave down on both sides of 0. Okay, and then we can use this information from increasing, decreasing, inflection points, concavity, to sketch a graph of this function. So again, I'm going to go ahead and just utilize Desmos for this. So let's see what we got here. We have y equals x to the 2/3, and then times 6 minus x to the 1/3. And this is our function. So look at these points of interest here. So we have a graph that is concave down and decreasing, leading into 0. At 0, we get the point 0, 0. Notice the first derivative and second derivative do not exist at 0 because it is a corner or a cusp. So then we have increasing and concave down. We hit our maximum at 4. And then we go still concave down and now decreasing. We hit that point at 6 where the graph does not exist, where the derivative does not exist. And this derivative goes from negative to negative, but the concavity actually changes. We go from concave down to concave up. We have an upward bend now for this last portion of the curve. And that is what this curve would look like.